Welcome back. This is Mr. Wakefield, and we're looking at section 7.3 at the moment, continuing on with chapter 7. In this section, we're going to be simplifying radicals, okay? Radicals of all different kinds of index numbers and whatnot. I want to make it really clear right off the bat that let's take a look at this example just so you can see what I'm talking about. Simplifying a radical does not mean that you just stick it into your calculator and say square root of 40 and then it gives you some answer. Okay, that's not, that would be evaluating the radical, all right? Just like we did in section 7.1 where you, what does evaluating mean again? It means to figure out what the number is that you square in order to get the number underneath the radical, all right? Figuring out what you square to get the 49. That's evaluating, all right? Figuring out what the square root is equal to. All right, well, we don't know what the square root of 40 is equal to. We know what the square root of 36 is equal to, and we know what the square root of 49 is equal to, but we don't know 40, okay? So if you get a number, usually if it's just like a normal whole number, like 1, 2, 3, 4, 5, one of those numbers, and it's not one of these perfect square type numbers here, you know, like 1 squared, 2 squared, 3 squared, 4 squared, one of those numbers. Okay, what's going to happen is your calculator is going to give you this big nasty decimal as an answer that is not even exact, okay? It's not an exact answer. It's rounded off. And so we're not supposed to give normally, we're not supposed to give a non-exact answer. We're not supposed to give a rounded off answer to any problem unless the problem says to round it off. So that's one problem with doing something like that. The other problem is that, again, that's not what simplifying means, all right? And we're going to talk about that. But and that's just the thing, though. All right, if you get some big nasty decimal, even if it was exact, that's not, you're not simplifying it. Some big nasty decimal makes it more complicated, doesn't it? So there's evaluating that we saw back in 7.1. Okay, where you figure out what the root is equal to, whether it's a square root or whether it's a cube root over here or a fourth root, whatever it may be. Okay, that is when you evaluate it and the radical actually disappears because you figured out what the root was equal to. All right, here we're not trying to figure out what square root of 40 is equal to. All right, now sometimes we will end up figuring out what it's equal to if it's one of these numbers, all right, even if they say to simplify it. But if it's not one of these perfect square numbers, the goal is to not evaluate it, all right, but to break it down to smaller parts here. As you can see here, they did in this problem. I'll explain how they did this in just a moment. Okay, but that's the goal here. So evaluating, you actually figure out what the radical is equal to, what the root is equal to, and then the radical disappears. Simplifying means to just break it down to smaller parts, and usually the radical will still be there after all that is said and done. Okay. Now, that's not to say that you won't have times in the future where when you get a problem like this that you wouldn't put it into your calculator. Sometimes you would. It's just that you don't do that when it tells you to simplify, okay? So that's what it means to simplify. It means to break it down to smaller parts. The radical will usually still be there, but it does not mean to just put it into your calculator, okay? So just wanted to make sure that was clear. All right. Now, before we go any further on figuring out how to simplify it, I want to make it clear what this rule says up here because we're going to use this. It says that if you've got two things, it doesn't have to look exactly like this, but if you've got two things being multiplied together inside of your radical, and that's all you have in there, just those two things being multiplied, then you can split the radical up into two radicals where those two things were being multiplied are also split. And now the radicals themselves are being multiplied. All right, we'll see plenty of examples of that. Don't worry if you're still trying to get a grasp on what that's saying. Okay, so here's how it's going to work here. All right, it says down here, simplify the following by factoring. All right, and we'll talk about what that means. And it says assume all variables represent positive numbers. Again, that means that we don't need any absolute values in these problems, okay? Because there won't be any issues with that when the variables are positive here, okay? At least in this case here. So in this first problem here, here's what you do. Okay, again, we don't care about what the square root of 27 is, but here's what we do. We take a look at our list up here, all right? This list up here, and we look at that and we say, okay, is 1 a factor of 40? Is 1 a factor of 27, which is the number? In fact, let me get this a little bit closer to the problem so we can see both things at the same time here. Give me just a second to do that. Here we go, right here. Yeah, we'll look at it right next to each other here. There we go. Okay, so looking at these numbers, these are the same numbers I have at the top of the page there, near the top of the page, and we've talked about these before when we did the a squared minus b squared factoring problems earlier in the semester back at near the end of chapter 5. Okay, is 1 a factor of 27? Yeah, it is, but what we're looking for is we're looking for the largest perfect square factor. Okay, the largest perfect square that is a factor of the radicand, which is 27 in this case. Okay, so we don't want just any factor of 27. We want the largest one that's a perfect square. So you got to look at the perfect square list, and it goes beyond 25, but I wasn't going to, it goes on forever, so I had to stop somewhere. But we know that the next one is 36, and then 49, and so on. Okay, we'll use those bigger numbers when we need to. But so 1 is a factor. Is 4 a factor of 27? No, it's not. Okay, 27 divided by 4 doesn't divide evenly. If it did, it would be a factor. It doesn't, so it isn't. 9, though, is a factor, isn't it? Because 27 divided by 9 is equal to 3. It divides evenly. All right. So is that the biggest one, though? Well, let's find out. 16, is that a factor of 27? No, it's not. Okay. 25, no, that's not either. And then remember, the next number is 36, but also remember that something can't be a factor if it's bigger than the number that you're looking at. So something can't be a factor of 27 if it's bigger than 27. I'm sure you've made many lists of factors in your life in previous math classes, and even in this one, you know that the list looks like this, doesn't it? Okay? Like that. You know that factors are never bigger than the number itself, 27, that you're looking at. And so if you once you get past 27 and go to 36 and 49, it doesn't even do you any good to look at those. Okay, so 1 and 9 are the what? They are the numbers on the perfect square list that are factors of 27. We are supposed to pick the one that is the biggest. Okay, do not do a number that is not on this list, though. All right, it's got to be something that's on the list. All right, now so you go through the list and then you find the largest one that is a factor. Just looking at the list, though. Now what you do is you take that rule up here at the top of the page and you use it to split this up. Now when you split it up, okay, you got to realize that if this is a square root right here, these two are square roots as well. Okay, if this had been a cube root, which we'll see later, these would both be cube roots. But since it's a square root, so will these be. All right, now once you split it apart, there's just one more step we got to do. Here's how it works, and I'm going to say this a lot, so don't worry. Okay, first radical you evaluate. Yes, we do some evaluating in this problem. It's just that you don't evaluate the original radical, that's all. Okay, the only time you'd evaluate the original radical is if the original radical was a perfect square underneath it. Okay, or all the parts of it were perfect squares. Like, for example, if this was just 25, that would be different. All right. No use in simplifying it when you can just evaluate it. But if it's not a perfect square underneath there, or any part of it's not a perfect square, then you got to actually go through this process that I'm doing right now. So we do evaluate the first part because that's the part that does have one of those numbers in it. So like I said, you can evaluate it, so why not? Okay, so you evaluate the first radical, and then you keep the second radical the same. Okay, and if you did it right, you guys, if you actually picked the largest perfect square factor, not just a smaller one, but the largest one, and if you did your math right and everything, okay, this number right here, square root of 3, you cannot simplify that any further than it already is simplified. And what I mean by that is, let's pretend like square root of 3 is like the original problem. Okay, let's pretend like we started the problem with square root of 3 and I said, hey, simplify square root of 3. Could you do that? Could you break it down to smaller parts? Well, the only factor from the list of 3 is 1. 4 and 9 and all those are too big anyway. But if I factor out the 1, like I did right here with the 9 and the 3, if I did 1 and 3, which is how that would work right there, okay, what would happen is that wouldn't make it any smaller, would it? Okay, it would just be 1 and 3. The 3 didn't get any smaller. The 1 is not going to make it smaller. All right, whereas the 27 did get smaller. We got 2 smaller parts, 9 and 3. That's what it's about. Okay, we want to break it down to smaller parts. Since 1 is the only thing I could factor out of that from the list, and since the 1 doesn't make the original number there, 3 doesn't make it any smaller, that then proves that this thing has been completely simplified, and you cannot simplify the leftover radical that you have, square root of 3, any further than it already is simplified. Okay, so here's the thing. You know that the radical you end up with is completely simplified like it's supposed to be if the number underneath the radical is such that the only thing from the list that you could factor out of it is 1. And 1's not going to do anything. So if that's the only thing you could factor out of the 3, you know the 3 is completely simplified. Okay. By the way, one other thing. Why did I put the 3 there up here in the first place? It's because this still has to equal 27. I didn't mention that. You may have figured that out. But so I knew that 9 was what I had to factor out. It was the largest perfect square factor. But I need to still make it equal to 27. So I had to put that 3 there. And let me make it clear. This has to be multiplication. Otherwise, we won't be able to use this A times B rule up here. Okay, so it has to be 9 times 3. All right. Okay, now let's try that again. This time with a variable. All right, but it's going to be very similar stuff here. When you have a variable, or pardon me, when you have a coefficient and a variable, that's 2 different parts there. And if there was another variable, that would be a third part, for example. Okay, so if you've got a coefficient and a variable, what you do is you look at those 2 parts separately here. All right. And start out with a 48 and ask yourself, okay, what is the largest perfect square? What's the largest factor from the perfect square list, in other words, that I could factor out of 48? I can factor 1 out of 48, but is that the biggest? I can factor 4 out of 48, but is that the biggest? 9 doesn't work, but 16 does. Okay, is anything bigger than 16 work? Remember, 16 times 3 is 48, so I know that 16 is a factor of 48. 25 doesn't work. You can use your calculator to help you with this. 48 divided by 25 is not a whole number, and so, in other words, it doesn't divide evenly. So that's how I know that. Your calculator will tell you that. 48 divided by 36, which is the next number, that doesn't work either for the same reason. The next number is 49, which is too big, right? So therefore, 16 is the correct number. All right. But before you figure out the part that's on the other side here, which we will eventually, I got to do the x to the 5th as well. Okay. So how do we do a variable? Here's how we do it. We need to pick, and we did this when we were factoring before, when we, like when we would factor out a GCF or something like that. Okay, you can't factor out something that is a bigger exponent than what you already got. All right, let me say that one more time. You can't factor out something that's a bigger exponent than what you already got. And so I can factor out x squared. All right, I can factor out x to the 4th, and I did do that when I was doing the GCF problems a lot of the time. Okay, you would never factor out an exponent that was bigger than any of the exponents you already had for that variable, which is why you always pick the smallest exponent in that case because it couldn't be bigger. All right, the smallest exponent was always the biggest exponent that was still smaller than all the ones that you had in those GCF problems. All right, so the point is that we need to pick the biggest exponent here that is still smaller than or equal to the 5. Okay, so x to the second is fine because it's smaller than 5. X to the fourth is fine because it's smaller than 5. Oh, but x to the 6th and x to the 8th and all of these are too big. Can't pick something that's bigger than 5. And so the biggest thing that I can pick that is not too big, in other words, the exponent's not bigger than 5, is x to the 4th. Okay, the biggest exponent that's not bigger than the exponent that you have. It could be equal to the exponent you have, but x to the 5th is not on this list, and so the next biggest thing was x to the 4th. Okay? Now, since I've now done the coefficient part, 16, and I've done the x to the 5th part, it's x to the 4th, I now what? I now need to figure out what to multiply by right there in order to get it's still equal to 48x to the 5th. All right, well, we know that since 16 times 3 is 48, 3 would have to go over here. And then since x to the 4th times x to the 1st, because when you multiply a term times a term, you guys, you have to add exponents. So 4 plus 1 on the exponents is equal to 5, and that therefore proves that it must be 3x to the 1st that we multiply by. All right? Once I figure out those two different parts inside the radical, the part that has all the perfect square stuff in it, 16 and x to the 4th, and then the part we still got to multiply by so that it's still equal. After we get those two parts, we then split this apart. By the way, you don't need to really write this dot right here. I do it, but if you have a radical right next to another radical, it's already going to be implied that you're multiplying them. So the dot's not completely mandatory there. But what did we do in the last problem after we split the radicals into two radicals? Okay, we evaluated the first one, the one that has the perfect square stuff in it from the perfect square list. We evaluated that one, and if you do it right, you should be able to because it has nothing but perfect square stuff in it. That means you can actually figure it out, figure out what the square root is. You don't even need a calculator or anything. Okay, and so what positive thing, okay, because remember a square root radical has to be positive answer. What positive thing, when you square it, is equal to 16x to the 4th? It would be 4x squared, wouldn't it? All right, 4x squared, just like we learned back in 7.1. And so there we go. All right, let's keep going here. When you don't have a coefficient, you guys, when we don't have a coefficient, it's just variables, then you can skip the coefficient step. Actually, there is a coefficient there. There's an invisible 1 there. But if your coefficient is 1, that's you don't have to do that part as long as there's a variable there. All right, just skip the coefficient part. You're not going to be able to do anything with 1 anyway. So we start out, and what happens is if you have multiple variables, you got to do each variable separately. Okay, so for y to the 5th, I picked the largest exponent from the list that's not bigger than 5. And then same thing with z to the 6th. I picked the largest exponent from the list that's not bigger than 6. Okay, so for y to the 5th, the largest exponent that's not bigger than 5 from the list is y to the 4th, isn't it? Okay. It's just a different letter right here, but the rule is still the same whether it's y or z as compared to x here. It's the exponents that we're talking about here that you can use y or z on this list here as well. Okay. How about for z? What's the largest exponent on the list that's not bigger? It could be equal, but it cannot be bigger than 6. Well, that answer would be z to the 6th, wouldn't it? Remember, it can be equal. It just can't be bigger than 6. All right. Now, so I did both y and z. I'm done with that part of it. What do I need to multiply by over here, though, so that it's still going to be equal to y5, z6? Okay. Well, we know that y to the 4th times y to the 1st is equal to y to the 5th, so y to the 1st would go over here. Now, since Z6 and Z6 are the same, though, you don't want to factor out, you don't want to put another Z over here, otherwise it wouldn't be Z to the 6th anymore. You'd have to add the exponents, and then it would be bigger than 6. Okay, we've seen this when we factor out GCFs out of polynomials in chapter 5, all right? If you factor out Z to the 6th out of Z to the 6th, you're not going to put another Z over here. All right. We then split it after we figure out those two parts. And then after I split it, like I did in the first two problems, I evaluate the first part and I keep the second part the same. What is the square root of y4z6? And again, you don't need absolute values here because it's already guaranteeing that the variables are going to be positive. So no absolute values needed. We get what? We get, wouldn't that be y squared z to the third? Isn't that the thing that you square? Just a little review from 7.1 right here. Isn't that the thing that you square right there to get y4z6? 2 times 2 and 3 times 2. Remember, when you got a term inside of a bracket taken to a power, that's when you multiply the exponents. When you got a term times another term, that's when you add the exponents. Just want to make sure there's no confusion there. Okay. There we go on that. All right. And so that is square roots right there, you guys. Now, what about cube roots and higher roots, you know, like 4th roots and 5th roots? The good news, you guys, is that the process is exactly the same. The only difference at all is that you need to look at a different list. Okay, if you have a cube root problem, wouldn't it make sense that we would look at the perfect cubes? Just like when we had a square root problem, we looked at the perfect squares. Okay, 1 to the third, 2 to the third, 3 to the third, 4 to the third. Okay, and then notice these exponents are 3 times 1, 3 times 2, 3 times 3, 3 times 4, and so on. Just like up here it was 2 times 1, 2 times 2, 2 times 3. Okay, and the numbers were 1 squared, 2 squared, 3 squared. All right, same idea. It's just that everything's now cubed with the coefficients, and then the exponents are 3 times 1, 3 times 2, 3 times 3, and so on. Okay, so same exact process. We still look at a list. We're just looking at a different list now. So now you got to ask yourself, what's the largest number on this list now? Not the square list, but the cube list that is a factor of 48. Let's try it. Is 1 a factor of 48? Yes. Is 8 a factor of 48? Yeah, it is. 8 times 6 is 48. Is 27 a factor of 48? No. And then the other numbers are too big for 48, aren't they? So the biggest one that was a factor was the 8. And since 8 times 6 is 48, I need to put the 6 there as well. And that's going to take me to what here? Let's see. Since you have your two different parts right there being multiplied together, you can now split it, and you need to split it. Please remember, you guys, when you split it, like I mentioned a few minutes ago, if you've got a cube root, it becomes 2 cube roots when you split it. A lot of students forget that. It's real easy to forget to write down those 3's, and that does matter because if you don't write down those 3's, they become square roots, don't they? If there's nothing written there, it looks like a square root, and then suddenly you've turned it into a square root problem, which it's not. And so you wouldn't be able to get full credit for that. All right, it wouldn't be correct. So don't forget those little 3's. Last step, like always, is you evaluate the first part and you keep the second part the same. All right, so what is the cube root of 8? As we learned in 7.1, that means that it is the number that you cube to get 8, and it is, of course, 2. Okay. Make sure that your 3 does not go too far out here beyond the v here. If it does, this will look like 2 to the third power. No, that's not what it is. It's 2 times the third root, or cube root, of 6. So make sure to keep that 3 from coming outside the v right there. Don't let it escape out there and go beyond where the v is here. All right. Okay. Same thing in problem E down here. All right. There's three parts here, though. Coefficient, remember you're supposed to do the coefficients separately, and you're supposed to do each variable separately. All right? Now, so we need to do this in three different parts now. All right, starting out with the 8. What's the largest number on the cube list, since I'm looking at perfect cubes? What's the largest number on the cube list? That is, actually, hold on, I need to, this will be easier to do. That way I don't have to zoom out so much. There we go. All right, now, there we go. 1 is a factor of 8, but so is 8. 8's a factor of itself, right? And then everything else is too big. So 8 actually would be the largest factor from the list, okay, for 8. All right. How about x to the 4th? Again, we want to pick the largest exponent that's not bigger than 4. 3 would be the answer, wouldn't it? Because 6 and 9 are too big. They're bigger than 4. So we want to pick x to the 3rd. Okay. Then for y to the 8th, what's the largest exponent that is not bigger than 8? Well, we got 3, 6, and 9, right? So it must be 6, huh? Because 9 would be too big. All right. Then after you figure out what all the stuff is from the list over here, for each of the three parts, you got to figure out what all that gets multiplied by to equal this. Well, 8 times 1 is 8. So I could write a 1 right here, but since I know I'm going to have a variable there, you know that when you have a variable, you don't need to put a 1 in front of it. It's already implied that there's a 1 in front of a variable. Okay, if I just say x, something like that, okay, there's already a 1, just like right here. We know there's a 1 in front of that x. And I know that I'm going to have an x right here because what does x to the 3rd have to get multiplied by to equal x to the 4th? That would be x to the 1st. Okay, and so again, you don't need to put the 1 in front of that, even though 8 times 1 is 8. All right, y to the 6 times what is y to the 8th? 6 plus 2 is 8, and so we're going to have y squared right there. Now that I've got my two parts, what do? I split it. Don't forget to bring down your little 3's. Okay. See, I did that on both radicals right there. And then keep the 3 inside the v there, though, that little v right there, so it doesn't look like it's in front of it. And then what do we always do? We evaluate the first radical, the radical that has the perfect cube stuff in it from the list, and then the second radical stays the same. And if you did it right, that radical should automatically be simplified already. So what is the cube root of 8x to the 3rd y to the 6th? Well, if I cube this right here, 2xy squared, all right, it would equal 8x3y6. So that must be the cube root then. All right. I just figure out that cube root the same way I did in 7.1 when we had a bunch of perfect squares and perfect cubes and all that inside of our radicals. All right. Okay, continuing on. How about fourth roots? Okay, well, let's talk about that for just a moment here. Don't look at the square list or the cube list, you guys, when you have a fourth root, all right? Because that's not what it is. For the fourth root, we have what we call perfect fourth powers. There's no cute name for it like square and cube, all right? Sorry about that. I just call it perfect fourth powers, all right? What are those numbers? They are 1 to the 4th power, 2 to the 4th power, which is 16, 3 to the 4th power, which is 81, and so on. Okay? For the x's, remember the x's, you guys, remember we had, for a square, we had multiples of 2 right here. 2 times 1, 2 times 2, 2 times 3. Okay, the cubes was 3 times 1, 3 times 2, 3 times 3. Well, it'd make logical sense then that our exponents here with the 4th powers would be 4 times 1, 4 times 2, 4 times 3, and so on. Okay? So that is the list we look at now. Otherwise, the process, once again, is exactly the same as it was in the previous problems. Okay, you're just looking at a different list, that's all. So 32, is 1 a factor of 32? Yeah, but is 16 a factor of 32? Actually, it is. 32 divided by 16 is equal to 2. It divides evenly, and so that means that 16, okay, would go in there. 81 is too big, and that's why I settled on 16 right there. I knew it was the largest factor of 32 from this list. Okay. How about y to the 11th? What's the largest exponent on this list that's not bigger than 11? Well, 12 is too big, but 8 is not, so it must be 8, right? Now that I've done both the coefficient and the variable that I have, what does that get multiplied by so that it's still equal? Whenever you simplify something in math, it's still got to be equal to the original problem. That's why I make a big deal about making sure it's equal still. 16 times 2 is 32. And y to the 8th times y to the 3rd, 8 plus 3, is equal to y to the 11th. After we figure out those two parts, we do the split. Like this. Okay. And we then evaluate the first part and leave the second part alone. Okay, and if you did it correctly, that should result again in a completely simplified radical. So what do you have to take to the 4th power to equal this thing? And just make sure it's positive. Don't say like -2. What is it? It's going to be 2y to the 2nd, isn't it? 2y to the 2nd. All right. That is the thing you take to the 4th power to equal 16y to the 8th. Second part stays the same, and we're done with that one. Okay, so that brings us to the last one here, which involves, as you can see there, it's a 5th root. So that means that, no surprise here, this is kind of going with the theme here. Since it's a 5th root, we're now looking at perfect 5th powers. All right, just like with the 4th root, we looked at perfect 4th powers. What are perfect 5th powers? 1 to the 5th, 2 to the 5th, 3 to the 5th. Thankfully, we don't usually get this big right here, okay? 243, and then so on, right? And then what about the exponents? Again, just like we had 4 times 1, 4 times 2, 4 times 3, for the 4th powers, the 5th powers are going to be 5 times 1, 5 times 2, 5 times 3, and so on if you need to go further than that. Okay. All right, let's try it. (96) is 1 a factor of 96? Well, 1 is a factor of anything, okay? The big question is there something bigger than 1 that will work? Is 32 a factor of 96, in other words? Yeah, it is, because 96 divided by 32 on your calculator would be exactly equal to 3. That means it divides evenly, since it's equal to a whole number 3. Okay, so I know that, don't forget to bring down that 5. I know that 32, all right, is going to be the thing that I'm going to use because the next number after 32 is bigger than 96. So I know that 32 must be the biggest one that actually works. What is the largest exponent that is not bigger than 4 from the list? Well, guess what? There isn't one. The smallest exponent is still too big for x to the 4th. When that happens, you guys, just leave x to the 4th alone. You can't factor anything out of it. Okay? If you can't factor anything out of it from the list, all right, then just leave it alone from the variable part there. Okay? How about y to the 7th? Well, y to the 5th you could factor out, and that is the biggest thing because 10 is bigger than 7. So we got y to the 5th. Okay, and then how about z12? Well, z to the 15th would be too big, but z to the 10th is not. So z to the 10th must be the biggest one that's not too big. Okay. So when I multiply this by something, what does this something over here have to be in order to equal the original problem? I know that 32 times 3, I know from saying 96 divided by 32 in my calculator, the fact that that's equal to 3, that means that 32 times 3 is 96. And so that's how I know that 3 is the correct number there. Okay, now remember, x to the fourth, since you didn't factor out an x at all, we kind of saw this kind of thing when we did GCF. If you have a variable that did not go in the GCF, all right, not that this is a GCF, but I'm just saying it's a similar thing because you're factoring it out. If there's a variable that did not go in the thing you factored out, then that entire variable and the entire exponent would then go into the second part because there's no x here to combine with it. So the x to the fourth is still completely intact. It didn't get broken down at all to smaller parts. Okay, so x to the fourth goes here. Y to the second goes there because 5 plus 2 on the y is equal to y to the seventh. And then, and I made a mistake there. I apologize, you guys. I meant to say Z10 right here. I think I'm pretty sure I said it. Correct me if I'm wrong here. Not that you can correct me over the video, but the point is that I think I said z to the 10th. I just didn't write it down, so I apologize if there was any confusion there. Z to the 10th, though, is the biggest number that is not bigger than 12. All right, so I meant to write that, and then that's going to make this what? This is going to make this z to the second right there. Okay. All right. So now that we know these two parts right here, all right, we do the split. Pretty big set of radicals this time, all right, but we're ready for the bigger problems here. Okay, we've done plenty of practice here. Now, like always, once you do the split, and don't forget to bring down the 5s, if you got a fifth root, then the two radicals that it splits up into must be that same root again. All right. What is the fifth root of 32y5z10? In other words, what taken to the fifth power up here? Let me zoom out so you can see that. What thing... I went the wrong way there. There we go. What thing taken to the fifth power is equal to 32y5z10? Wouldn't that be 2 to the fifth gives you 32? And wouldn't y to the first give you y to the fifth, 1 times 5 on the exponents? And wouldn't z to the second, 2 times 5 is 10, wouldn't that give you z10? And so that means that the fifth root is 2y z to the second. Again, the second radical stays the same, and we've simplified that one. So you can see that the process is the same no matter what kind of root you got, whether it's square root, cube root, or something bigger, but you just got to make sure that you are, and this is the big thing, the biggest thing of all, make sure you're looking at the correct list. Do not look at the perfect square list if you're doing a fifth root, okay? Make sure you're looking at the correct list. All right. What I'd like you to do right now is flip over to the back side, and I need you to just do problems 1 through 5. You can see that 6 through 8 look a little bit different. We're actually going to do those together here at the very end. All right, they just involve an extra step that I still want to talk about. Actually, you know what? I'll do number 5 with you as well. That's kind of different. Just do 1 through 4 before you hit the play button once again. 1 through 4, and then we'll do 5 through 8 together. All right, so 1 through 4, and then hit the play button. All right, guys, let's take a look at square root of 28. We know that the largest exponent, pardon me, not exponent, the largest number from the perfect square list, since this is a square root after all, for 28 would be 4. And so we want to get 4 times 7 right there. All right, 4 times 7. We then split that. And then as usual, after you split it, you evaluate the first radical. Okay, what is the square root of 4 in other words? What is the number that you square to get 4? And it's got to be a positive answer because it's a square root radical. That would be 2, of course, right? So 2 square root of 7. Problem number 2. All right. And by the way, if you don't factor, and this is not an issue here necessarily, but if you don't factor out the largest perfect square, again, you're going to end up with a radical that's not completely simplified. It'll be a radical that'll have a number in it that you can still factor something out of from the list besides 1, okay? It won't be completely simplified if you don't pick the largest stuff from the list, okay, for each coefficient and for each variable. All right, so just want to make sure that we're understanding that, how important it is not to just pick anything that works, but pick the largest thing from the list that is actually a factor. All right, number 2. We got to look at these two parts separately. 40, what's the largest thing from the list? It's a factor of 40. Well, as it turns out, it's going to be 4. Okay, but what about x to the third? The largest thing from the list that's not bigger than 3 would be x to the second, wouldn't it? All right. And so we got 4x to the second. And so what does that multiply by? That is multiplied by 10x, isn't it? To get it still equal to the original problem. Okay. We split that. And then we evaluate the first radical. We get 2x. Okay. And there you go. Let's keep going here. All right. There's a reason why I crossed this thing out. This was actually correct, okay, when I wrote down there 27 times 2. That is correct, but I just want to show you something here. You can actually skip a step now that we've done this enough times. I think you can see here from the first 9 problems that we've done is that I can just jump down here, okay? It's still going to be the same 2 terms after I split it apart, and so it's inevitable that I'm going to split it apart, so might as well just jump from 40x to the third all the way down to here, right? Because you know that it's going to be the same 2 terms coming down, and you know that this radical is going to split, all right? So you can skip that step. That's what I'm saying here when I cross this out. So you can just go straight to that if you like. If you still want to write down this step because you're still not completely comfortable with skipping that step, that's fine, no doubt about that, but you're welcome to skip that step now. But once we got them split apart, what does that mean? It means that I, again, evaluate the first radical and I keep the second one the same. Just like we've been doing all along. Number 4, okay, x to the third and y to the 15th. Those are the things that I can factor out of x to the third and y to the 17th. Why did I not factor anything out of z squared? It's because the smallest exponent on the perfect cube list on the front side of your worksheet is z to the third. But that's too big for z squared. That means that all the exponents are too big, and when all the exponents are too big, do not factor anything out of z squared. Okay? So then that means that in order to get these things to still equal to each other, you got to multiply by y squared z squared. Okay. Now that I've split it, I evaluate the first radical, and I get xy to the 5th, because that's the thing that you cube to get x3y15. And then the other radical, of course, stays the same. So that is 1 through 4. All right. Now, let's take a look at 5 through 8 together here. Okay. Let me go ahead and get the clean sheet of paper back out here. All right. Now this one's a little bit different because we haven't seen a bracket with 2 terms in it in one of these problems yet. Okay. What I want to point out though, let me write this down off to the side because it's going to be similar. It's not the same, but it's similar. Pretend like that bracket is a variable. Oh, sorry, that came off the screen. There it is. Pretend like that bracket is a variable. How would this thing simplify? Well, if it was z to the 4th, wouldn't we want to factor out z to the 3rd? Because again, that's the largest exponent that's not bigger than 4 from the cube list. That means that z to the 1st would come over here. And so our final answer then, we evaluate the first radical, we get z to the 1st. The second radical stays the same. Okay, what I'm pointing out here, you guys, is when you get one of these brackets taken to a power inside the radical, if they ask you to simplify it, what they want you to do is the same thing we did with the z. You take the bracket to the third power, just like I took the z to the third power. You factor that out, and then like we found out in the 7.1 section, if you have the cube root of a bracket to the third power, if these two exponents are the same, it's going to be end up being equal to this right here. And you need to keep that bracket there, okay, because it's got two terms and we're multiplying it by this radical over here still. This radical needs to stay the same. You can actually get rid of this bracket inside of this radical because, as I said in the last section, if you're on the inside of a radical, I'm not talking about the outside here, but the inside, and all you have in there is just a bracket, nothing else inside of there, you can get rid of that. But this bracket you cannot get rid of because it's got two terms. You got two terms in this radical answer over here, and you're supposed to multiply this entire answer from the first radical by the entire second radical. So if it's got two terms, you got to bracket it. Okay, it's different when it said the two terms are inside of the radical because the radical is kind of like a bracket in and of itself, and so that contains the whole thing. All right, but if it's just a normal polynomial like x plus y, you can't just put the x plus y next to the radical without bracketing it because that entire thing is being multiplied by the radical. Okay, so a two-term polynomial, we've seen it many times before, it's got to be bracketed if the whole two-term polynomial needs to be multiplied by something else. All right. Okay. Moving on here. 6, 7, and 8 are different because we actually have radical terms being multiplied together. And let me explain what I mean by radical terms, all right? When you got a radical, you guys, but then it has a term in front of it that's being multiplied by it, this is all a radical term, including the 3. I know that the 3 is not inside the radical, but it's still a part of what we call a radical term, all right? So in a similar way, even though the 6 is being square rooted and not the 5 is still a part of the radical term. It's not being square rooted, the 5 I mean, but it's still part of the radical term. What I want to point out here is that when you have a radical term times another radical term, the way you multiply those together is you multiply the outside parts and then you multiply the inside parts. Outside times outside is 15, and guess what? Outside times outside, that answer stays outside the radical. Inside times inside, 15 times 6 is 90, and that stays inside the radical. Okay, so let me say that one more time. A radical term times a radical term. Outside times outside stays outside. Inside times inside stays inside, and we created a brand new radical term here. They now want us to simplify this resulting radical term. And you might be thinking, well, wait a second. What do I do with the 15 right there? We're going to talk about that. Don't worry. Okay, but let's simplify the square root of 90 first, and then I'll deal with the 15, okay? By the way, since we do have to deal with the 15, go ahead and keep bringing the 15 down with the answer that you get from the simplifying the square root, okay? So what would happen if I simplified 90? The largest perfect square factor, the largest number from the perfect square list on the front of the page. Okay, I'll go ahead and pull that out once again here. All right, that largest number is going to be 9, isn't it? Okay. Remember, the list does not end at 25, but if we went beyond that, okay, you would see that 9 is still the biggest one that works. Okay. So 1 and 9 work, but we need to pick the largest one. So we get this, don't we? All right. By the way, if 1 was the only number that worked, okay, suppose the 9 didn't work and 1 was the only one that worked, that means that the radical is already simplified and you don't need to simplify it. If 1 is the only thing that works, and that includes the variables as well. If 1 is the only thing that works for the coefficient, and then the variables, none of those work at all, then that means the radical is already simplified. And we'll see some of those coming up here as we go along here. Not necessarily in this section, I don't think, but some future sections. You'll see stuff like that. Okay, so after we split this, what do? We evaluate the first radical and we keep the second one the same. But if we have a number that was already previously outside of the radical term there, and you can see that this is a radical term up here, because you got a regular term being multiplied by a radical. Notice I said multiplied. It's just like with regular terms, all right? If you've got a regular term being multiplied by a radical, not adding or subtracting, but multiplying, that's still a single radical term there altogether, even though it's got multiple parts to it. It's because it's being multiplied. Okay, so just wanted to clear that up too. But notice here that we have a regular term being multiplied by a radical term right here. The regular term was just coming on down the 15. That was just coming down each step. And then the 90 turned into a radical term, a different radical term than it originally was, 3 rad 10. When you have a regular term being multiplied by a radical term, what you do is you multiply the outside parts. Outside times outside stays outside, just like it was up here. But then since the square root of 10 does not have another radical to get multiplied by, then it would just multiply onto the end. It wouldn't change at all. Okay. So regular term times radical term, just multiply the outside parts, and then the radical just comes on down. Okay. Let's take a look at the last two right here. Notice in this one right here, you have a radical times a radical. That's also a radical term times a radical term. It's just that there's invisible ones in front of each radical here. Invisible ones in front of each one. Okay. So you could still multiply outside times outside like I did in the last problem when we did 3 times 5. Okay. It's just that if both of them are equal to 1, it's not going to do anything, is it? 1 times 1 is 1, and then I still got to do the radical part, and so I'm going to end up with what? I'm going to end up with 24x to the 11th on the inside of the radical. Remember, inside radical times inside the radical stays inside. 15 times 6 equal to 90. Inside times inside stays inside. Same thing here. The inside, 2x to the 7th, times the other inside, 12x to the 4th. That answer stays inside. So that's the reason why you don't need to do it if it's just no number in front of each radical. It's because 1 times 1 is 1, and I don't need to write that 1 there when there's a radical after it. We already know that there's an invisible 1 there when you just have a radical sitting there. Okay? And so, again, yeah, if you have no numbers in front of the radical, then just multiply inside times inside, and then that would stay inside. Because the 1s are not going to do anything there. Okay. If one of these radicals had a number in front of it, but the other one didn't, that would be different, and we'll see that. We'll talk about that in the next section here. Okay. But when they both have nothing in front of it, then that's what we do. Okay. Then, just like in the last problem, after we multiply the radical terms together, we simplify. So just more of the same stuff here. What's the largest number on this list right here? Oh, sorry, it came off the screen there. What's the largest number from this list right here that is a factor of 24? That would be 4, wouldn't it? And then what's the largest exponent from this list that's not bigger than 11? Well, we got 10, and then the next one is 12, isn't it? So 10 would be the largest one that's not bigger than 11. Once I figure out what all my perfect square stuff is that I factor out, what is that 4x to the 10th getting multiplied by to equal 24x 11? Wouldn't that be a 6x, like that? And like usual, evaluate the first part, keep the second radical the same, and there you go. One more, you guys. One more. This time we got cube roots, but the idea is still the same. As long as they're both the same index number. You cannot multiply a cube root times a square root. But if they're both the same index number, you are allowed once again to do the inside times the inside. Okay, so what is this term times this term? And again, inside times inside stays inside, doesn't it? So 54 x to the 11th, y to the 13th. Okay. And so what are we going to get there? How do we simplify that? Remember, we got to simplify after we multiply. That's what the directions said on the front when it said the directions for these problems. What is the largest number from the cube list, since this is a cube root problem, that is a factor of 54? That would be 27, wouldn't it? Okay. And then what about the x part? Well, 9 is the largest exponent that's not bigger than 11 because the next number is bigger than 11, x to the 12th. So x to the 9th is the one you want to choose there. Okay. And then finally, what about y to the 13th? What do I factor out of that? 12 is smaller than 15. Pardon me, I'm getting ahead of myself there. 12 is smaller than the exponent we have, 13, but 15 is too big. So 12 must be the largest exponent that we can use there, okay, from the list. All right. What does that get multiplied by here? 2, x to the second, y to the first, in order to get it to still be equal to the previous radical up there. Okay. All right, now, what are these radicals equal to? Or pardon me, what am I saying? Sorry about that. Just like always, you guys, I lost focus there. Just like always, after we split the radicals, we what? We evaluate the first radical, and we keep the second one the same. Nothing different. So we got what? We've got 3 x to the third, y to the fourth. That's the thing that when you take it to the third power, okay, it's going to be equal to this thing right here. And so that's the cube root. The second radical, as we said, stays the same. And that, you guys, is how you simplify radicals. We're going to be seeing plenty more of that in the next couple of sections, so make sure that you understand that concept and let me know if you don't, all right, prior to watching the next video and moving on to the next section, okay? But yeah, like I said, if you've got any questions or concerns, as always, let me know, and you have a good day. You take care.